Good morning, all. In continuation to our discussion on image enhancement, let us discuss nonlinear transformation. And today we will discuss logarithmic transformation. The general mathematical equation for logarithmic transformation, it is S equals to C log 1 plus R, where R is my input intensity level, S is my output intensity level, and C is constant. The general question arises for logarithmic transformation, it is why don't we prefer this equation S equals to C log R? Why don't we prefer this equation S equals to C log R for logarithmic transformation in image enhancement? So using this equation for logarithmic transformation in image enhancement, the problem arises when my input intensity R it is equals to 0. So when R equals to 0, in this equation, in place of R, if we substitute 0, the equation of S becomes C log 0, and we know log 0 is undefined and hence S is undefined. So using this equation, when input intensity it is 0, my output intensity it becomes undefined. So to avoid this kind of situation, in order to overcome this kind of situation, instead of using this equation, we preferred S equals to C log 1 plus R for logarithmic transformation in image processing. Now using this equation, if the same situation arises, that is my input intensity R equals to 0. Now in this equation, in place of R, if we substitute 0, the equation of S become S equals to C log 1, and we know log 1 is equals to 0, so S become equals to 0. And hence for logarithmic transformation in image processing, we widely prefer this equation S equals to C log 1 plus R. Now in today's discussion, we will use this equation S equals to C log 1 plus R in order to plot the transformation curve for an 8-bit digital input image. For an 8-bit digital input image, my n is equals to 8. Total number of gray labels, that is L equals to 2 to the power 8, and it is equals to 256. Now their representation, 256 number of gray label, their representation is, it starts with the gray level 0 to the maximum gray level, that is 255. So for an 8-bit image, our input intensity level will vary from 0 to 255, and we want our output intensity level S will also vary from 0 to 255. Now in order to plot the transformation curve using this equation for an 8-bit digital input image, we have to compute the value of C. So in order to determine the value of C for an 8-bit digital input image, we will apply the boundary condition when R equals to 255, S is also equals to 255. Now in this equation, in place of S, I will substitute 255. In place of R, I will substitute 255, and we will determine the value of C. So the equation become, in place of S, I will substitute 255. So it is 255. It is equals to C log. In place of R, I will substitute 255. So it is 1 plus 255. If you simplify this, it is C log 256. And if we rewrite this equation, then the equation becomes C equals to 255 divided by log 256. And if you simplify this expression, it is 105.886, and if you approximate it up to 2 decimal place, it becomes equals to 105.89. So we have determined the value of C for a 8-bit digital input image. It is 105.89. Now we will substitute the value of C in this equation and we will obtain the equation of S for an 8-bit digital input image. So this is the equation of logarithmic transformation for an 8-bit digital input image. Next, we will plot the transformation curve for this equation. Similar to the previous, along x-axis, we will take the input intensity level R. Along y-axis, we will take the output intensity level S. For an 8-bit image, the value of L, it is 2 to the power 8, that is 256. Now we will mark our critical points. First, this is my origin. Next, this is L by 4. This is L by 2. This is 3L by 4. And this is L minus 1. Now, if L equals to 256, L by 4, it is 64. L by 2, it is 128. 3L by 4, it is 192. And L minus 1, it is 255. Next, we will mark the critical point along this y-axis. This one is L by 4. This is L by 2. This is 3L by 4. And this is L minus 1. Now, if L equals to 256, L by 4, it is 64. L by 2, it is 128. 3L by 4, it is 192. And L minus 1, it is 255. Next, we will draw a simple table. This side, we will write R, that is my input intensity level. And this side, we will determine the output intensity level S. And the equation of S that we obtained, it was 105.89 log 1 plus R. Now the value of R that we will take, first it is 0. Next one, it is L by 4. If L equals to 256, L by 4, it is equals to 64. Next L by 2, that is 128. 3L by 4, that is 192. And L minus 1, that is 255. Now for each value of R, we will determine the value of S. First, when R equals to 0, in this equation, in place of R, we will substitute 0. So the equation of S, it becomes equals to 105.89 log 1 plus 0. If you simplify this, it is 105.89 log 1. And we know log 1 is equals to 0. So this expression becomes equals to 0. Next, when R equals to 64, in order to determine the value of S, in this equation, in place of R, I will substitute 64. So the equation becomes 105.89 log 1 plus 64. And if you evaluate this expression up to 2 decimal place, it is 191.97. Next, we will round off this floating point number to its nearest integer number. So 191.97, its nearest integer number, it is 192. Next, for R equals to 128, we will determine the value of S. For the same, in this equation, in place of R, I will substitute 128. So the equation of S, it becomes 105.89 log 1 plus 128. If you evaluate this expression, up to 2 decimal place, it is coming to be 223.49. Next, we will round off this floating point number to its nearest integer number. So it becomes 223. Next, For r is equals to 192, we will determine the value of s. For the same, in this equation, in place of r, I will substitute 192. So the equation of s becomes 105.89 log 1 plus 192. If you evaluate this expression up to 2 decimal place, it is 242.02. Next, we will round off this floating point number to its nearest integer number. So it becomes 242. Next, for r equals to 255, we will determine the value of s, and for the same, in this equation of s, in place of r, we will substitute 255. So the expression becomes 105.89 log 1 plus 255. If you evaluate this expression up to 2 decimal place, it becomes 255.01. Next, we will round off this floating point number to its nearest integer number, so it becomes equals to 255. So for each value of r, we have determined the value of s. Next, we will plot this. So the first point, when r equals to 0, s is also equals to 0. R equals to 0, s equals to 0, represent this origin. Next, when r equals to 64, s equals to 192. When r equals to 64, s equals to 192, tentatively represent this point. Next, when r equals to 128, s equals to 223. When r equals to 128, s equals to 223, tentatively represent this point. Next, when r equals to 192, s equals to 242. When r equals to 192, s equals to 242, very closer to L minus 1, tentatively represent this point. Lastly, when r equals to 255, s is also equals to 255. So lastly, when r equals to 255, s is also equals to 255, tentatively represent this point. Now we will connect all these points. And this curve, this is the curve of logarithmic transformation. For an 8-bit digital input image, and we have used the equation of s, it is equals to 105.89 log 1 plus r. So now let us analyze this curve. When r varies from 0 to 64, in the input side, when my difference is 0 to 64, my difference is 64. In the output side, the difference is 0 to 192. So in the graph, you can see 0 to 64 represent 0 to 64 represent this region. This is nothing but my dark region. It is expanded to 0 to 192. So in logarithmic transformation, we are expanding the dark pixel. Now in the input, when R is varying from 192 to 255, the difference here it is 63. In the output, the intensity level, it is varying from 242 to 255. The difference here it is only 13. So in the plot also you can see when R varies from 192 to 255, this is my bright region. In the input, my difference it is 63, and in the output, my difference is only 13. So in this case, I am compressing my bright pixel. So once again, when my input is varying from 0 to 64, the difference in the input side it is 64, but in the output I got the range 0 to 192. It means we are expanding this dark pixel. When the input it is varying from 192 to 255, the difference here in the input it is 63, but in the output the difference it is very narrow, it becomes 13. It means we are compressing the bright side, or that is we are compressing the bright pixels. So since we are expanding the dark pixel, in output, after performing the logarithmic transformation on digital input image, in output we will get a bright image output. Or in other words, after performing the logarithmic transformation, our output image becomes brighter. In logarithmic transformation, the mathematical equation of logarithmic transformation, it is s equals to c log 1 plus r, and in book the logarithmic transformation curve, it is represented by this nonlinear characteristics, and we have plotted this nonlinear characteristics just now. Next, this is a small project work. I made it in MATLAB in order to understand the application of logarithmic transformation. Image A, it is my input image, and in this project work, this input image A, it is first converted into its frequency domain, that is by applying the Fourier transformation. Now this FFT spectrum, it is decentralized in nature. In the next step, I make it centralized. In the centralized spectrum FC, you can see a dot, and the remaining region, it is very dark. And in order to enhance this dark region, I have applied the logarithmic transformation, and as a result I obtained this output image S, and in this output image S, clearly we can see the dark region are significantly enhanced. This is the project work. I made it in MATLAB, and this is the example which is given in the book. This was the input image, and in order to enhance the input image, logarithmic transformation has been applied, and as a result the dark region has been significantly enhanced. So in this lecture we have discussed the logarithmic transformation. In our upcoming video lecture we will solve some numerical question. In our upcoming lecture we will solve some numerical question based on logarithmic transformation. Today I am going to stop here. If you have any suggestion, if you have any doubt, you can write it in the comment section or you can write email to me. Till then, happy learning, have a nice day, and thank you all.